So my topic in this case is going to be swimming. So we're going to switch a little bit of environment. And what I'm going to talk about today is a paper that we recently published in Science Robotics. So all this work that I'm going to present is actually a teamwork. So it's a lot of people along with me involved in this project. So just keep it in mind. And I'm going to do my best to summarize to the key points of our work because, well, we did a lot. We have a lot of conclusions, a lot of nice findings. But yeah, it can be a long talk. So I decided to go to the main parts of this paper in that way if later you are curious about to see, it's going to be easy to drag our tools and the paper itself to understand better. Okay, so the title of the paper is Emergence of Robot Self-Organized Undulatory Swimming based on local hydrodynamic force sensing. And to start this, okay, the motivation of all this project is actually in animals. During this process of this paper, we did certain applications and certain visualizations to explain better how do we start with these motivations in biology. And I would like also to take the moment to share some of these visualizations, some videos that we did in order to also well, give to the journals and to the public to better understanding of this paper. So the motivation, I'm going to use a video. I hope if you don't hear, please let me know.
Let's start by taking a closer look at how animals, like the lamprey, swim in the water. They do so by sending waves of body bending from head to tail. Thereby they accelerate the fluid backwards and the body forward. From previous work, we know that these waves are generated in the animal's spinal cord, which is part of the central nervous system. Here, groups of neurons, called neural oscillators, generate the corresponding rhythmic muscle activations that eventually lead to undulatory swimming. In contrast to the central, there is also the peripheral nervous system, which is made of sensory neurons that provide information about the state of the body and the environment. In this study, we were interested in the lamprey's ability to sense the surrounding fluid as it moves. More specifically, we were interested in understanding the pressure forces along the body as the body swims through the water.
Okay, so this is just a tiny screenshot from the video because I want to remember this part. So all the talk and all the work is based on these two main parts, which is the spinal cord and the sensory neurons. And it's interesting that long ago, there was a debate while trying to understand how vertebrates generate locomotion in people who support the idea the spinal cord is the main generator of the movement, and people who support that sensory feedback or the reflexes are the ones that dictate the movement. Okay, so in order for us to collaborate with these two parts, so this debate was long ago. Different people support different parts, and now there come more research into how these two interact. And our work is mainly in that. We want to understand how these two parts are able to work together in order to generate locomotion. And for that, so our work is based on the assumption of what I said, that we are using that both the neural, in this case, the spinal cord and the sensory feedback, the reflexes, both collaborate between both of them in order to generate the locomotion. So for that, we use a model that you can see on the left. Okay, something that, well, you know, we're assuming that the body is composed of 10 segments, and each segment has a specific model. So I'm going to go directly to the model because it's quite important for me that you understand. So we have our oscillator. The oscillator is composed of couplings that allows the connection with the other oscillators. Those oscillators command signals to the muscles in order to generate movement. And the part that we are adding to this is that we have some feedback, in this case on sensors. So knowing that this is one of the key important parts that you keep in mind, let's continue. Okay, yeah. Oh, sorry, why am I coming back? So we go now to the mathematical model. So these two first parts is what we know as a CPGS. So this is work that it's been done quite long ago, especially in my lab in BioRob. We work a lot on CPGS, so in this part on the left. And the part that we are adding here with this work is the part on the right, that is the feedback. Okay, so this term in here is the intrinsic frequency. So we are talking about the oscillator, the one that we have here in the middle. Then we have the part of the coupling, that is these arrows that you see here. So it's this term on the middle. And then this last part, we are talking about the sensors. And one of the important parts is that this part goes to this U signal, which is the activation signal. And this activation signal goes to this equation here, that is the one that actually commands the activation of the muscles, okay? So as you know, we need to have certain contact with interaction with the environment. So in this case, we look for this torque, that the torque is composed by an activation signal given by the CPG and plus the feedback that we have here. We have certain stiffness and we have certain damping, okay? Sorry. So now we come up with this idea of local feedback. So before starting any experiment, we start running the robot. So just position control. So the only difference that we have a low amplitude in the head, large amplitude on the tail. And here in the first part, we have some snapshots of, in this case, simulations, but both experiments were done in the robot and in simulation. Sorry about this, I forgot to mention, everything that I'm gonna show from now on, we did it both in hardware and in software, okay? And in here, the arrows, what you can see is the forces, that is the environment is exerting in the body. And so in here in B, the line, the dark line that you see here is the angle that each of the models have. And the colors represent the value of the feedback. In this case, the force. As you see, the first signals have a low angle in amplitude, and the last one has a large amplitude. And when you compare the dark signal with the colors, we can see that the trend is the same on both. So we can say that the feedback is actually quite related with the movement. So, okay. And something really interesting about this is that if you pay attention in the 10th model, there is a little shift between the color and the line in black. So there is certain shift, which is already telling us more information about how these two are related. So in here, we decided to plot this phase lag, this shift difference. And we can see that there is a little angle that actually represents this shift. If we don't have this angle, then what we will see was a line, but in this case, you can see that there is a tiny slope that is also related with that when you send traveling signals from head to tail, you are going to have this as you see here we start the peak and we see a diagonal, okay? And the speed that we get between them. So the most important part here is that we have a shift between the two signals, and that is now what I come back again with our equation, and it's because is how the system works. So we have a sinusoidal signal here that is affected by the force. And what we assume is that this force has a shift. So it's gonna make that the whole signal at the end is gonna be affected in some way that is gonna make it move further or slower in this case. So why I'm saying this is an introduction of a concept that is actually the main topic or a key element in the work, that is entrainment, okay? So now I'm gonna move to explain what is entrainment. So I'm gonna mute and I hope you get the video. Sorry about this. Before the entrainment part, I'm gonna, sorry about this. I'm gonna explain how we decided to test this equation. So for that, we create our undulatory swimming robot, which is Agnatax. Here we see the chain of motors. The motors are composed of different motors. These motors goes inside a swimming suit to protect all the electronics. And outside, we have this sensory feedback that in this case are load cells, each one in one of the sides. And here we have the circuit. And on top, we have some styrofoam because the sensor itself creates some load that make the robot sing. So in order for us to compensate that, we make it flow with the styrofoam. And the final result is here, the robot. So now, again, this is now the part of the entrainment. So the entrainment is how the controller works. And the main principle is that, as I explained you before, that we have a sinusoidal signal here and it's affected by a force. And this force generates a shift that you saw it in the previous slides. And this is how we come with the key element that is entrainment. So now I'm going to show you.
Entrainment is a well-known phenomenon present in many fields from biology to engineering, in which coupled oscillating systems interact with each other and are driven to a coordinated state with a common frequency.
So what I was talking is about the term entrainment. That is that, as an example, imagine that you have a pendulum. I'm sure maybe you have seen this kind of exercises, that when you have a pendulum and you have a line and then you put multiple pendulums across the same line, at some point all the pendulums synchronize. Okay, so this is the effect of entrainment. And in our case, we are synchronizing, but only in frequency. Okay. I'm really sorry about these technical issues. We have a super nice video that explains with animations all this entrainment process that is way better than explaining by words, but it's more visual. But yeah, if you have time, please take a look at the video. So now I'm giving you all the tools to now understand the results. And the last part before going to results is the configurations that we test. So here we have the 4 configurations. The first one is only the CPG. That, okay, this Graham-Brown's configuration and Sherrington configuration was that long ago I explained you that there was a debate. So this was the first person that started this debate in towards that the locomotion in vertebrates is mainly done by CPGs, and Sherrington was in this configuration that is oscillator free. So CPGs, as I said, there is no feedback. So in this case, we don't have the black line here. And when we translate in here, it means that in the equation, we don't have this element on the right. The decoupled part, it means that we don't have this black arrows connection between the oscillators, which means we don't have this element on the middle of the equation. Now, oscillator free means that we don't have the CPGs. So it means we don't have frequency here. So we only have this part of the equation without this one. And combined is when we have the whole equation, okay? So with that in mind, now I'm gonna switch with the results. The results, we also did a super nice tool for visualization for people to go and play by themselves with all the configurations and all the possible results. I'm just gonna give you an introduction to this tool, and hopefully later you get the chance to play by yourself with this tool. And okay, I'm gonna start with a video. Actually, I didn't put videos in my presentations, but here you can see the robot. It's quite nice when you see it swimming underwater. Yeah, you can see the sensors that we have on the side and all the electronics that it's really below the robot. So this is the introduction to the site. Now you say here in the corner, you can go to Go Interactive site. And here we have 4 different results that we got. So I'm gonna start with the most important one and relevant probably, which is neural disruptions. So in this one, remember let's go first to the right, the 4 configurations that I told you. So now we are gonna generate some lesions, in this case to the controller. That means what happens if some of the sensors are muted, what happens if some of the couplings, so we have a total of 10 couplings, for instance. What happens if we remove the 6 and the 7 or the 1 or the 9? So we were randomly selecting this. And when you see here in the plot, you have 0, 3, 6, 9. The 9 represent the number of lesions that we create, okay? So when we say 9, it means that only 1 in this case is working, okay? And the same, so also when we muted some of the oscillators, so translated to the animal means literally that something happened to this part of the body, to this sensing, for instance. When you see that some of the results here, there are start dark and then goes to white color, that means dark, it's high robust. That means that it has a lesion, but this lesion doesn't allow, in this case, the simulation and the robot can still swim despite of this lesion. Okay, so it means it's better for swimming. So the darker, the better. So let's start with, for instance, the decouple, where we have, what we can see here in the top videos that when we have zero neural disruptions, of course, we are swimming. And when we go low, we can see that the speed is reduced. The speed is the left axis in all our results. So the speed is reduced, but still can swim. So now let's go to oscillator free. So we can see that the first simulations are able to swim, but we can see how clearly the last ones, they stop working. When we go to combine, it means we are having into account all the, remember the equation, all the parts of the equation. We assume that it's more robust, and this is where we actually see that the result is actually quite dark, the block. And when we see all the examples, we see that all of them are actually swimming. And what we can do with, I can let you later play if you want to see, but the most important part is that if you, for instance, go to this one, that is below, we can see that only the first part is dark, which means if we see the videos, makes sense, only the ones that has a low number of disruptions are able to swim, while the more disruption is basically stop swimming. And what's something important to see generic, that if you see all the column of combine, most of the column is basically dark, meaning that we are getting conclusions that by using all these peripheral plus the CPGs, we are able to get more robustness into the swimming. So now I'm gonna come back. Okay, something I probably can highlight here. So now I'm gonna show you the entrainment, just to be more specific in one of the cases. And the video I'm gonna show you is actually, imagine this, let's say this blue dot in here in comparison with this blue dot in here. Why I'm saying this, because actually this plot is a really huge amount of experiments. So, and each of them represents a different video. So it's quite a lot of data. So I'm just gonna focus on this one, in this two. So it means when one of the controllers have actually all of the neural disruptions. So now we're gonna go here. So as you see here, without feedback means that we are having 9 neural lesions, you know? So as you can imagine, intuitively say, if you are full of lesions, it's hard to swim. And this is what you are seeing here. Well, when you don't have these lesions, you are able to swim. That is what is happening on the right. So something that I wanted to show you with the video that unfortunately we couldn't hear is that these circles that we see in the middle is actually easy to understand when all of them are synchronized, when all the emergence of the behavior. So when you see here in this side on the right, you can see these dots that appear towards all the line. So when there are all of these fast movements of the dots, it means the movement is already synchronized. Well, here you can see that the dots are all over. They're really no pattern, which means there's no synchronization. So this is just an example. And now with oscillator free. So this is, in this case, we have the feedback, but the feedback is too small. So it means we are able to swim, even having this small feedback in comparison with the fast feedback. The difference is the frequency. So as you see here in the left, the movement is really slow, while in the right, the movement is quite fast. And well, again, we can see the synchronization dots in here. So this is an example of the entrainment. Now the robot experiments. This is actually quite nice to see. Let's start with the decouple. So you can see that the robot it has an initial condition that we don't know. It's a random initial condition. So you can see that the signals are all over the place. Once at certain point, oh God, the video just stopped. Okay, but you can still hear. Maybe we can see again. So we don't see any pattern in the signal, which means that we don't have swimming, but at some point in the video, the signals are already aligned. So you can see this diagonal, and we can see effectively the robot is swimming. So we can see how the controller takes some time to actually activate, to create this emergence of the movement. Now let's go with oscillator free. The same at the beginning, we don't have anything, but this actually, we can already see that some controllers or some configurations are easier to create this, the final movement, while others takes longer. And again, the combine is our best case. So we expect basically be swimming already from the beginning. And this is what we got with the robot, that actually makes sense with our assumptions. So this is, okay, this is some tests that, that actually are interesting, because as you see here, the difference between these two is that, for instance, in the left, we don't have the head nor the tail. Why I'm saying that? Because sometimes when you are swimming, the fact that you have a huge head and a tail, that already creates the locomotion. So while doing this test, what we want to do is create symmetry in the body. So we are not saying we have this big head or we don't have the long tail to help to generate this locomotion. So we create these after results just for this kind of questions, like what we will get if we don't have the head, or how much the head is actually affecting on the tail, to have that general swimming behavior. And okay, this asymmetry, now let's go to this side, is because the first one, okay, I hope I don't confuse people, but when you are activating a joint, actually your muscle is before, you know, so we have the muscle and after we have the joint itself. So basically what we are doing that is here. Before we used to have the feedback on the same oscillator. Now we are saying that the oscillator is in the segment before, okay? So the segment before has the feedback, and this feedback is moving the segment after. This is based on what we see in muscles, is what I'm telling you. So again, this is just experiments that we were wondering what happened under these cases. In the big case, what we are doing is that this feedback is now affecting the same segment. Actually, it's affecting the previous and the next segment. Okay, it's affecting both. So we are not saying it's affecting only the next. Now we are saying it's affecting both. In C, okay, it's the case that we know. So this is when it's affecting the same. And in this one is when now it's affecting two segments after, okay? So let's say we are in the oscillator one, so we are affecting the joint number 3, okay? And our case E is when we go 3 segments beyond that, okay? So if we are working in the segment 1, we are affecting the segment number 4. Okay, so this is just a test that we wanted to do, just to show you that, yeah, we can generate some swimming in some of them. And yeah, it's just matter to start qualitatively comparing that there are some difference in the level of the signal, okay? And well, this is just to give you a quick overview in all the results. The tool itself is quite handy and easy to use for people who has curiosity in each of the cases, because present each of them is actually quite a lot of information. And with that, I think I'm going to start finishing. So, okay, we have a lot of conclusions with this work, but I want to go for the main two that I would love that you keep in your mind. That is that peripheral mechanisms leads to self-organized undulatory swimming by providing intersegmental coordination. So we are talking about the coupling, and body oscillation, talking about the frequency. A combination of both central and peripheral mechanisms offers a higher robustness against neural disruptions that won't happen if we just play one alone, okay? So this potentially explains how some vertebrates are able to move after spinal cord lesions. So in this case, we are talking also in the engineering side, so the robustness after system failure, okay? Which is also quite nice as a robotic application. So this work also gives some future paths, like for instance, we explore only exteroceptive. So we believe that if we go to proprioceptive, we're finding another redundant source of feedback to the swimming and CPG. And something nice is that this kind of platform, this robot farm, the robots can be used to test additional motor control hypotheses that are difficult to study in intact animals. And with that, I would love to finish, and thank you.